Hello, everyone. Welcome to week 5 of the term. I'm Professor Rios. This week, two slide packets available going over the materials of moisture and water balance and weather systems. So now we're primarily addressing tropical cyclones and, of course, mid-latitude cyclones. Okay, so let's begin with part 1. Basically, don't forget to look inside the folder for the to-do list. Make sure that you know what to do by the end of this week. You should be good to go. So let's get going on the first part. So moisture and water balance. Okay, and moisture, water vapor, H2O. Remember, the only substance that can exist in all three phases on Earth, basically simultaneously, depending on latitude. It is responsible for absorbing and releasing latent heat when phase changes. So that's a key important term to remember back to previous lessons. These are the different objectives. So how moisture is measured, what is an air mass, and how they can be classified, methods of lifting air to form clouds, and so on. So these are the key terms for the lesson. We'll get into, again, this one here and this one here. Really, all of these are essentially repeats or retreads of a previous lesson, but definitely worth highlighting again. So moisture has obvious significance. It affects your cell phone signal. It affects television signal, traffic, air travel, of course, visibility. It has to be used for planning. It's a very significant variable of everyday weather, whether it be rain, snow, fog, or simply cloud cover. Most of the water in the world is ocean water, seawater. Of the water that is not ocean water, most of that is basically caught up in ice sheets in Antarctica and Greenland. So the real small part that we humans really rely on is that little tiny sliver of the overall amount of fresh water. So it's obviously the most valuable resource there is, more so than oil and other fossil fuels, because it basically drives everything. So now, you'll know about the fate of moisture. You've seen this to some extent in many, many classes, earth science and so on. But water doesn't last long in the atmosphere. It gets recycled a lot. It falls into the ocean, it evaporates, it forms into clouds again, it falls as rain or snow in mountains, fields, lakes, deserts. Really, it's recycled pretty regularly. Although you don't have to remember this specific number, water lasts about 9 days in the atmosphere before it goes back. That's not a very long residence time, okay? So that's the idea of the hydrologic cycle. In terms of air and temperature, so warm air has a higher capacity to contain moisture within it versus cold air. Cold air, all the little oxygens and nitrogens, this is what you breathe, is mostly they're compact, and as a result, there's less space for these little H2Os, whereas warm water is less dense, so it's more spread out, and as a result, there's more space for the little H2Os. Notice, when is it that you experience dew or frost? It's always in the morning when it is cold. So condensation ends up happening as a function of cooling, and usually condensation happens in the morning. In fact, it always happens in the morning because that's the coolest part of the day almost exclusively. All right? So that's the idea of warm versus cold air. Again, you breathe N2 and O2. This makes up about 99.2% of what you breathe every second of every hour of every day of your entire life. H2O is very variable, so it depends if you're in Florida or if you're in the desert. obviously that has a variable nature to it. We talked about latent heat, the idea of the state, the phase change in water, whether you're condensing or evaporating, which is frankly what we're mostly associated with here, vaporization and condensation. It involves the absorption or the release. If it releases heat, it warms the environment. If it's required to absorb heat in order for it to happen, like when evaporation takes place or vaporization, then the net result is you feel cooler. But that's latent heat. Think of the term latent. It happens after something else happens. Evaporation. Evaporation is simply the phase change from liquid to gas. So that when you put a pot of water on your stove, and it will vaporize. Eventually, it'll reach the boiling point, and you'll see steam coming out. That's evaporation. Evapotranspiration is the combination of basic evaporation, but also what you gain as a result of plants, land, soil, and other such sources. So if you're in the middle of a city like New York on a hot day, it's going to be a lot hotter in Fifth Avenue or the middle of one of those busy streets than it is going to be in Central Park, because Central Park has land, soil, and water, so the evaporation tends to cool you down. Okay, so that's that idea. Condensation, of course, is the opposite, the phase change from gas to liquid. It is affected by those three factors that you see there. Condensation nuclei is something that is in the middle of every single water droplet in the world. They tend to be little bits of stuff: dust, smoke, ash, pollen, salt. And they provide a surface around which water can condense, forming what you think of as a raindrop or a water droplet. Okay, if you think about fog is made up of a whole bunch of really, really, really small and very, very light water droplets that can float. Okay, once water droplets begin to coalesce and collide and become bigger, they become raindrops. And of course, they fall down to the earth as what you expect as rain or shower or something. Okay? Cloud droplets will grow as they collide and stick together. So the measures of humidity. There are three basic ones that I want you to focus on. Two of these you're probably somewhat familiar with. The other one, maybe not so much. So specific humidity is nothing more than the actual water vapor in the air, the quantity, the weight of it, the density. So it's the amount of water vapor per kilogram of air. So if you have a kilogram of air with no water in it, and you put in a certain few grams of water, it's those few grams divided by the total volume that you have. And so basically the maximum specific humidity increases with increasing temperature. Think back to that one graph. So therefore, you can have high specific humidity values in places like the Amazon and in places like the Caribbean and in the tropical oceans, unless as you go north into colder and colder and colder climates, which are basically considered deserts. Relative humidity is an interesting feature because it's relative to the amount of water that could be held for a specific temperature. So it changes throughout the day. The best measure of moisture is frankly dew point, and that is the temperature at which saturation happens, or dew. Get it? Dew point. You have to reach a certain temperature, meaning you have to cool to a certain temperature before you saturate. So as temperature increases, the vapor capacity of that particular air mass will increase as well. We've touched on this quite a bit already. This is not really from your book, but I really do like this graphic, which is why I provided it to you. At 4 in the morning, your temperature might be 41 degrees and your humidity is 100%. That means your dew point is also 100%. Get it? Temperature at which dew happens. So if it's 100%, it's saturated. The dew point is also 41%. But notice by 10 a.m., your temperature has gone up to 61, and your humidity is lower now. But your dew point hasn't really changed. You can think of the dew point as the little blue square. Notice the same at 4 in the morning as it is at 10 a.m. as it is at 3. The only thing that has changed is what? The temperature. It went from 41 to 61 to 90. So what that means is that this cold air had a small capacity to hold moisture, so it became saturated and dew formed. By 3 o'clock in the afternoon, it was much hotter, and therefore the air could hold this more moisture, this much more. So the humidity is only 20% because it's holding only 20% of what it could hold for this temperature. So it's variable. So the relationship is, as the humidity increases, your temperature decreases, and as your temperature increases, your humidity decreases. And this is during a typical sunny summer type of day. Obviously, as weather systems move in and out, this will change. Talk about the idea of a cloud. So we'll get into that. Clouds are made up of water droplets, which each inside has a condensation nuclei. Already mentioned that before. And these are the types of clouds. You tend to have high clouds, middle, low, and then what are called clouds of vertical development, like a big thunderstorm. Okay? And again, that's a more visual representation, whereas this is more of a name chart. This might be a little bit easier to sort of see. And you've seen these little wispy clouds way up high. You've, of course, seen a thunderstorm, those big, thick, tall, vertically developed cloud systems. Moisture. So we're talking about the idea of types of precipitation. So you're used to, snow and rain, but there's other types. Hail, usually associated with thunderstorms, and sleet, which is not to be confused with hail. Sleet is what usually falls in winter and spring when you have snow that begins to fall and it melts, but it freezes before it completely melts. And so you get this like a little slushy ball falling to the ground. Water balance. So your book talks about the idea of potential evapotranspiration. So if your potential evapotranspiration is greater than your precipitation, then you're going to lose water, right? So if your rainfall was 2 inches for a month, but you had so much of this that it accounted for 3 inches of water that was evaporated, then you've lost water and you have a desert. When P, precipitation, is greater than potential evapotranspiration, there is a water gain. So think about the jungles of the tropics, okay? So it really depends on which climate you're talking about to think about. Now, in some places, this is seasonal. So in some places, you may have a dry season, so this applies. And then you may have a wet season, this applies. And then you can do the whole month-to-month evaluation and see if you have a surplus or a deficit for the year. Okay? And here are some examples from your book. Here's the city of Tokyo, Japan. Notice they are in surplus the entire year. This is Baghdad in Iraq, where they are in deficit for a big 1, 2, 3, 4, 5, 6, 7, 8 months of the year. Here you have a place like Portugal, Faro, Portugal. So they have a deficit 1, 2, 3, 4, 5 months of the year, and they have a surplus 1, 2, 3, 4 months of the year. So it's a seasonal thing in many places. Here in New York, we're in surplus the entire year. We're like Tokyo. which is why we have so few droughts in New York. Air masses. What is one? Don't say it's a mass made of air. That's not the definition. An air mass is something that is large, it's uniform and distinct, and it's so in terms of temperature and moisture. Okay? Air masses tend to assume the characteristics of the places they came from, called source regions. So typically, air masses will form where you tend to have areas of pressure that doesn't change much. Think about the Sahara Desert. Think about the Arctic tundra. Think about the equator. Places, think back to that global circulation model where you have one of those L or one of those H's over it almost the entire year. Okay? So now, you can break up air masses into several types, basically 6. You have a small letter M or C for maritime or continental. And then you have large letters E, T, P, or A, equatorial, tropical, polar, Arctic. And so in winter, we're typically in this air mass here in New York. Every once in a while, we will have this. And we have this when it becomes like 0, when it's below 0, that kind of air. In the summer, we tend to have this air mass quite a bit. But we go between this air mass and a modified version of that air mass in summer. We never get this. We're too far north to receive this type of air mass. But you get that in the Caribbean, like places like Puerto Rico, maybe South Florida, maybe extreme South Texas, that area of the country. Okay, you tend to find continental tropical. This is very hot, dry. West Texas, New Mexico, Arizona, the Mexican desert, the Mojave Desert, Sahara, middle of Australia. So it's a pretty simple graphic, dry, wet, very wet, hot, warm, cold, very cold. Okay. These are the ways of lifting air to form clouds. So convection. Convection is, again, air, warm, liquid, fluid bubbling up. So think about that summer thunderstorm that forms suddenly. That's an example of convection. Here is a very good example of convection. Can you see it? You can literally see in this image here the air going up, the air going down, the air going up, the air going down, the air going up, and so on. It's like popcorn. If you're a pilot or if you're in an airplane going through this, you feel it. You feel the plane like vibrating. That's convection. Frontal is, the front is the one doing the lifting. And so with a cold front, you can have cold air moving on warm air. And during a warm front, you have warm air moving on cold air. This one is, cold air is lighter, so it has a more difficult time pushing cold air out of the way. Cold air is heavy and denser, so it has an easier time pushing warm air out of the way, which is why you tend to have the more severe weather associated with a cold front than you do a warm front, generally speaking. Orographic, remember this back a couple of lessons ago, the idea of forcing air up and over a mountain. That is called orographic lifting, or lifting due to topography, or, it goes by several names, okay? And we gave the example of last week, the image from Google Earth that had basically Western Oregon, the city of Eugene, wet, rainy, and then Bend, Oregon on the other side of the Cascade Mountains, very, very dry. We talked about the adiabatic process. So again, a lot of this stuff is review from the last couple of weeks. Again, a heating or cooling that takes place solely as a result of pressure changes, okay? So when the pressure goes down, the temperature goes down. We talked about the idea of relative humidity being less than 100%, lifting the air at the dry adiabatic lapse rate, forming a cloud eventually, and then being saturated and cooling, but at a lesser rate because you are releasing latent heat into the environment. Okay, and again, there's the mountain, there's the air being forced, moisture being released, cooling, air sinking, compressing under higher and higher pressure, drier. So this is the windward side, this is the leeward side. All right? And this we did last week, so I am not going to go over this again. If you want to, you can review the material. So I am going to, let me hide that again. And we're going to get into convective thunderstorms and what they look like. Again, this is an example of convection. Okay, there's a very, you don't have to be a meteorologist to realize that's a thunderstorm right there. Okay, and that's what it looks like. It begins as a small puff. It begins to grow. You have air going up and down, and eventually lots of heavy rainfall, maybe briefly, 30, 40 minutes. Okay, and here's the idea. You need a moisture source, and that moisture source is an air mass that is maritime tropical, usually during summer. Topography can help it along, so you can have a storm moving up and over a mountain, so it provides a bit more lift to that air. And this is where you tend to find convective thunderstorms, and this is depicted as a function of lightning. So notice where you tend to find lightning. Near the equator, Africa, the three big tropical rainforests. You do find them, of course, in other places, but it kind of shows you where you have warm water. Notice how there's very few in the Pacific out here off the California coast where the water temperatures are colder. Okay, and notice how you don't really find any out in the Arctic or in the Antarctic. So it's mostly in the middle of the earth where it's significantly warmer. Tornadoes, well, here you're talking about, of course, a cyclone. It's a very small storm compared to like a hurricane or anything like that. Extreme low pressure. Again, winds have been clocked as strong as 318 miles per hour. That's typically the size, tens of meters to a few kilometers in size. And so it's a function of different air masses that are clashing. And as a result, you tend to find the majority of tornadoes in the United States and Canada. So here is where you find the majority of them. And we have the perfect geography for tornadoes in the United States. You have a moisture source in the Gulf. You have a cold source in the Canadian tundra. You have the Rocky Mountains providing like a fence. And the middle of the country from North Texas, Oklahoma, Kansas, Nebraska, and this whole region is more susceptible to tornadoes than really anywhere else on Earth. Notice tornadoes are not a thing near the equator by and large. That's because you do not have the air mass contrast. It is all warm, moist air in this area. And that is the first lesson packet. We'll get into the second one a little shorter. So this one is about weather systems. So these are the objectives for the lesson, for this particular part of the lesson. The ingredients necessary for cyclone formation, and so on. So their significance, well, humanitarian relief. These are some of the more iconic hurricanes that have affected mainly the Atlantic. And so my list is very Atlantic-centric. Hugo, that affected South Carolina. Andrew, that affected Florida. Honduras, Mitch in 98. Katrina and Rita in 2005, which did so much damage to New Orleans. Sandy in 2012, which affected New York. Harvey, Irma, and Maria, and then Michael in 2018, which is the last Category 5 hurricane to affect the continental United States. It hit the Florida Panhandle. So tropical cyclones, hurricanes, same thing. Tropical cyclone is a more generic name. Hurricane is a name given in the Atlantic and the Eastern Pacific. It comes from the Puerto Rican, Taino, Indian god of the wind called Huracan. And so that's sort of where it comes from, and it's been sort of adopted. Hurricanes are born north and south of the equator, but not at the equator. Coriolis comes into play. They are fueled by massive amounts of latent heat of condensation, providing excess heat. This is inside the hurricane eye wall of Katrina. So aircraft do fly into these things. And these are the ingredients. So this is one of the homework questions. And these are the answers. Warm water, that's the first ingredient you need. You need to have water that is 26.5 Celsius or warmer. Coriolis, you need to be away from the equator. That's for the spin. You have to have a pre-existing low. Think of it as a little seed. And no significant wind shear, which is basically a change in wind direction with height. Wind shear would literally slice off a storm if it's too strong. So imagine a little disturbance moving through the Atlantic, and then latent heat is released, convection continues, the surface pressure drops, the gradient, remember that from a couple lessons ago? So the gradient gets stronger, so the winds get stronger. The storm remains organized as long as you have warm water available and the wind shear isn't bad. And it usually dissipates when it moves over cold water or it goes inland. That's it. That's how a storm usually. Now they can become big, heavy rainmakers inland. So it doesn't mean they're done, but the strong winds are usually done inland. Okay, so this is an example, an image here. It's showing you where you do tend to find hurricanes forming. Notice none at the equator. Look, none. None where there's cold water. Okay. They tend to be more stronger. They tend to be more frequent and stronger in the Pacific because this is where the hottest ocean waters are found. By the way, the island of Guam is like right about here. They get on average 4 storms a year. This is how they tend to move. So they will move with the trade winds when they first form, and then they will essentially move and turn to the north and northeast as soon as they are affected by the westerlies. And you see it here. East, west, east, west, east, west, and then at some point, turn. Some of these east, west, east, west, east, west, north, northeast, northeast. So not every hurricane does that, but the majority of them do that. So this is showing you the global circulation model affecting hurricane tracks. So this is 1999. This is the SAFFIR-Simpson scale. So when you hear about Category 1, Category 2, what does that mean? It's really talking about wind, and it's talking about damage. So that's what the categories really mean. The categories are based on damage. And damage is not just wind. Obviously, that's the most obvious, and heavy rainfall, but storm surge, okay? And so storm surge is the idea of not only is it lower pressure so the water can be higher up, but then the winds are pushing that water inland, okay? Now, in the case of, this is Hawaii, this is New Orleans during Katrina. Oh, here you're talking about the idea, unfortunately, of levees that broke. So it's a bit of a human-aided problem. And here's the effect of water, the power of water. This building used to be here, and the water literally took it and moved it. This building used to be here. And then this is a plank of wood that literally sliced through that palm tree. That's the power of wind. This is also the power of wind. This is what Hurricane Andrew did in Homestead, Florida. Typically where hurricanes and storms hit for the most part, so areas that stick out, Florida, North Carolina, New Orleans area, Cape Cod. Areas that stick in usually are affected less. So, hurricane season peaks are on September 9 to 10, and the reason for that is the fact that water has a high heat capacity. So it takes water a while to heat up. So it takes water up until about September for it to reach its maximum temperature, and therefore the maximum amount of energy that's available for them to realize. And you want to turn that water energy into wind and rain. That's right, the heat engine. Hurricanes, of course, are an environmental insecurity issue. They each, on average, cost about $1 billion, but many of them cost way more than that. They affect all these things from coastal populations and infrastructure to premiums, oil and gas, major ports, the economy, obviously. Katrina still remains the deadliest storm in United States history, costing $250 billion. And again, it affected New Orleans significantly. That's what New Orleans looked like. About 80% of the city flooded. The other type of storm that I wanted to address is the idea of a mid-latitude cyclone. That's a different storm than a hurricane. A mid-latitude cyclone is the contrast of warm air and cold air, whereas a hurricane is all warm air. So a mid-latitude cyclone is what we get here in winter, right? We may have 60 degrees, it feels nice and warm, you may get a rain shower, and then the front moves through, the temperatures drop, and the rain may end the snow. You might get an inch or two of snow. That is a mid-latitude cyclone. The constant up and down of temperature, different air masses. That cold air is coming probably from Canada. This warm air is coming down from the Gulf. In the equator or the tropical regions, this never happens. It's always warm. And if you're way up at the poles, it's always cold. In the area of the world that we live in, we tend to have constantly changing air, which is why in January you can be 5 below zero, and a week later you could be 55. And then a week later after that, it could be 0 again. Get it? So it's highly changeable, okay? And this gets at the idea of cold fronts have more severe weather associated with them. Warm fronts tend to have more gentle weather across. So this line from here, through here, through here is this. So this point here is here. This is this. This is that. So it's like cutting a cake and seeing the different layers. And that is it for the lesson. Next week, we get into climate and climate classification, not climate change, just climate. So having said all that, I hope you have a great rest of the week. If you have any issues, let me know. And I can get with you during the live office hour and or separately if you want that. Otherwise, best of luck, and we'll talk to you soon.